Hey everybody, this is Dawson, and we are going to be doing a little bit. This is the one of the extended assignments. So those of you who are interested in pushing yourself a little further, we're going to take this square root stuff a little bit further and really see what we can make you do. So this episode is on extreme square roots, otherwise radicals, otherwise known as radicals. So square roots is the more common name, but oftentimes if you're actually talking to mathematicians or people who know math pretty well, they'll talk about square roots as radicals. So in this video, I'm going to throw those two names around so that they are interchangeable for you and you can start getting used to that terminology. Okay, so radicals and square roots. Now, the reality is that we are setting things up fairly simply right now. We're trying to just get the point across that when you have the square root of a number, let's say it's 25, square root of 25, you're looking for a number times itself that will make that number. So the square root of 25 is 5 times 5, or 5. And so what we want to be able to do, though, eventually is be able to work with these numbers a little bit more complicated and be able to simplify them and really start to think in terms of what does it mean to be a square root and how can that have an actual value to it. So we're going to play with that a little bit today and really be focusing on simplifying square roots or radicals. All right, so here's an example for you. We got a line here, and we've been talking about this in class, and we've been talking about this in your homework and things. And so we have seen this kind of tilted situation where you have the line that is going up at an angle. It goes through a couple points. It's a little harder to figure out the length of this line, and that's where the square roots come in. And we know that if we can find the area of this square off of this line, then we can find the length of this side by taking the square root of it. And so this is a little tricky, but I kind of have used that idea of a ratio. So we go over 1, 2, 3, up 1, 1, 2, 3, up 1. We can also look at it as over 1, 2, 3, 4, 5, 6, up 2. So I'm going to do that. I'm going to go start my line here. I'm going to go up 6, but then over 2. And that's going to get me my new line. From here, go over 6, and then down 2 to this point, down 6, over 2, back to my original spot. So now if I can find the area of this square, then I know I can find the side length just by taking the square root of that side. That's a lot of squares to count. We could certainly do it. It would take a little bit of time, but we could start blocking off these whole squares, figuring out these little chunks and things. But I want to remind you that we've already done this. So we have already found the area of the square that has a 3-to-1 ratio here. This little 3-to-1, just this little chunk of it we have figured out already. And so if we look back in your notes, you'll remember that this is the square that had the triangle that was a 1 to 3 side. So that this little piece in here was 1.5, and you had another 1.5 up here in this area, and then there was another 1.5 up in this area, and another 1.5 over here. So if we added up all those 1.5s, that was 2 of them would make 3, 2 more would make 6, plus you had the 4 in the center, so this one here gave us an area of 10. So this is an area of 10 in here. And let me go ahead and just write that in. So this area was 10. And so if we know that, well, this is 10, and this is 10, and this is 10. So I'm just going to speed this up a little bit so we don't have to count all those squares. Quickly here, you can just say 10, 10, 10, 10. I know that the area of this square in total is going to be 40. So between all 4 of these, between all 4 of these squares, we have an area of 40, which means the side length of this square is going to be, you should know this, the square root of 40. That's really bad. 0. Square root of 40. All right, now that we know that, that's all good, but square root of 40, that's pretty darn big. You can ask yourself, is that a perfect square? Well, let's see. We've got 4, we've got 9, we've got 16, we've got 25, we've got 36. That's getting close. But that 6 times 6 is 36. 7 times 7 is 49. So this is not a perfect square. It's between 6 and 7 somewhere. So we're kind of stuck at this point. But not really. We can actually take things and go a little bit further with them than we have already, if we know how to simplify radicals and work with radicals in that way. Now I'm going to take out a few things here, and I'm going to have you think about this in a slightly different way. We already talked about how we have known this piece of the line. We've already figured that out. We know the area of that is 10. So there's the area of 10. And then we know that this other one is exactly the same, this other piece, and that's exactly half of that line. So that's 10, and this one's 10. So the area of this is 10, and the area of this is 10. So we know that from this piece to this piece right here, maybe I'll just do it up here. From here to here, this side length is the square root of 10. And so is this one. This is also the square root of 10. And so to find the length of that line right there, we can add square root 10 plus square root 10. So I'm going to start writing over here. Square root 10 plus square root 10 will also give us this side length. Okay, now this gets a little trickier. What do I do with this? Can I add square roots together? Can I add radicals together? This is kind of crazy. And it turns out that you can, of course. That's why I'm doing this video. And what I want you to be able to see is that if you think about when we did the combining like terms, and we saw x plus 2x, and we had x plus 2 more x's. How many x's do we have? We have 3 x's. If we just have x plus x, we get 2 x's. Because there's 1 x here. This is that hidden number 1 in front of that, and there's 1 x here. There's a hidden 1 there. Turns out there's a hidden 1 in front of this, and there's a hidden 1 in front of this. You can think of these radicals kind of as variables, as long as the radical matches. Because remember, if I had x plus y, I can't do anything with that. I can't simplify that anymore. I can't combine them because they are different. But because these radicals are the same, just like x's, I can put them together, and I can call this 2 square root 10, because it's 2 square root 10s put together. 1 plus 1. 2 square root 10. So I'm adding together these numbers in front. So let's take another example here. Let's say I had, oops, sorry about that. 4 square root 3 plus 2 square root 3. Well, these square roots are the same. They are the same value right here. And so we can put those two together. We can say, well, gosh, that's 4 of them. 4 square root 3s. And this is 2 square root 3s. If we just pretended it was 4x plus 2x, you would probably, at this point, because you've done this for a while, and hopefully your brain isn't too rusty on this, you would say, oh, easy, 6x, no big deal. Well, it's the same thing here. This would become a 6 square root 3, and that's it. You're done. You can put those two together because they are both square root 3s. That is perfectly legal, and it simplifies things nicely and makes it good and clean. The problem is it still doesn't answer this interesting dilemma that we have here, where we combine these two together. Yes, that's true. 2 square root 10, and that's great. I'm going to get rid of this so we've got some more space to work with. But it doesn't answer how 2 square root 10 could be equal to square root of 40, because that's basically what we said. We said that this line here, because we figured out the area of this whole big square, would be square root 40. And these both are square root 10s, which we figure is 2 square root 10. So how could this be? How could we have 2 square root 10 be the same thing as the square root of 40? That just is doesn't look right, right? Because we know we can't put these together, 10 and 40. That doesn't work. So how is this going to happen? Well, it turns out you can do some interesting things with these square roots. So let's look at the square root of 40 and figure out how that part works. Square root of 40. Okay, now 40, it's a big number. It has many factors to it. It has many factors inside of this. 2 is a factor of 40, 4 is a factor of 40, 5 is a factor of 40, 10 is a factor of 40. Lots of factors inside of this number. And it turns out we can actually break up the 40 into factors if we want to. So for example, we could say that the square root of 5 times the square root of 8 is going to equal the same thing. Is going to equal the square root of 40, because it's going to be 5 times 8. When we put those together, 5 times 8, that'll get us 40. Oh, okay. So that's interesting. And so we could also say that the square root of 40 is equal to the square root of 2 times the square root of 20. That would also work, because those are both factors of the square root of 40. So, okay, that's all right. The problem is that that's not going to help us any unless one of these factors is a perfect square. None of these factors are perfect squares. If you remember, our perfect squares are 1, which aren't going to help us in this situation because square root of 1 is just 1. 4, 9, 16, 25, 36, and so on. And they just keep going up. So if you look at the square root of 40 and you think about its factors, let's go ahead and write them out. We got 2, and we have 4, and we have 5, and we have 10 are all factors of 40. I mean, actually 20 is also a factor of 40. It's getting pretty big, but it's there. We look at this list of factors. Are any of those perfect squares? Well, yes, in fact, there is one. 4. 4 is a perfect square, and it's also a factor of 40. So if I wrote that out as the square root of 40 equals square root 4, and then because that's my perfect square, I want to use that one, and I have to multiply that by the other factor that would get me 40, and that is the square root of 10. Okay. Still, you're kind of wondering, I'm guessing, where are you going here, Dawson? I don't see anything happening. But what's the square root of 4? Oh, 2 times 2 is 4, so the square root of 4 is the whole number 2. So the square root of 40 equals 2 times the square root of 10. Okay, multiply in algebra, we often are just able to drop that sign. Square root of 40 equals 2 square root 10. We have now changed the square root of 40 to the 2 times the square root of 10. If we go back and look at our original problem, guess what we had? 2 square root 10. And so we can see now that this actually, oh, that's not what I wanted to do. We can see now that this is exactly true, that the 2 square root 10 is equal to the square root of 40, because we just showed it through our work here from this point down. So this is our proof that that is true. We can split these up as factors, take the square root of 2, we get 2 times the square root of 10, and then you get 2 square root 10 as your simplified version of the square root of 40. So, very long answer, but you've got a couple ideas now. You know how to add together radicals, and you also know how to simplify radicals now. So there's two things that you've learned, which is great. So now let's do one more thing before I sign off for the day, and that is to have you combine radicals or add radicals together that at first glance don't look the same. They look a little different, and it might get you thinking that that they can't be put together. So let's look at an example. 2 square root 6 plus 3 square root 24. And so we have a situation here where these two do not look the same. These two radicals are not the same. Therefore, we cannot add these two together yet, because as it turns out, this radical over here can be simplified. Sorry, I just messed that up. These radicals over here, this radical over here, 3 square root 24, can be simplified. So let's take a look at that. 24. 24. What are the factors of 24? Well, we have 2. 2 goes into 24. We have 3. That goes into 24. We have 4. That goes into 24. 5, no. 6 goes into 24. Yeah. And we have not 7, not 8. And I'm sorry, 8 does go in there. Sorry, that is 1 in there. And so, you know, that's probably pretty good. 9 doesn't, 10 doesn't, 11 doesn't, 12 does. So we could put 12 in there if we wanted to as well. So these are our factors. And we can keep going, but these are going to be the most important factors. And so, well, let's take our list. Any perfect squares here? Oh, there's our 4 again. Oh, that thing keeps throwing up a lot. So here we have 2 square root 6, and for I always write them all out again or else I get confused, plus 3 times, and I just put that in there to keep myself straight, square root of 4 times the square root of, and 4 times what is 24? It's 4 times 6, so 4 times the square root of 6, okay? This part's going to simplify, right? Square root of 4 is 2. So we go back to the beginning, 2 square root 6 plus 3 times, now this turns into a 2 times square root 6. And I know some of you will be able to do this faster, especially as you get better at it, but I really want to show all the steps here before I go any faster. So 3 times 2 is 6. So 2 square root 6 plus 6 times the square root of 6. Remember, we can just drop that times. We don't need it. And hey, look at this. Now these match up. They are both square root 6. We can now add them together. So then the answer would be 8 square root 6. And then, even though at first it didn't look like they would go together, in fact, they can go together once you simplify this radical. All right. Well, that's all I'm going to show you for today. So you'll have a chance to play with that a little bit and work on that instead of when you're done with the test and things like that. You can work on this as a way to challenge yourself. Excellent job for listening, and I hope you learned something new.